So we're recording. Here we have a graph that I've made with some fake data. Okay, so we've got the angle of the mousetrap in this column here and the average velocity in this column here. I haven't put units with those, but those units are meters per second and the angle is in degrees. Now, as we look down here, we can see that, I'll just show us how we created that graph. So we select the entire set of data, we click insert, we go down to over to the right here, and we click the scatter plot option there, and that will give us angle versus velocity there. I'll just delete my old graph if you'd like. And now with that graph, what we can do, okay, is we can create a trend line. So if we select our data there and we right click or double click, depending on whether you've got a computer or a Mac, you can add a trend line. Now if you look on the far right of our screen here, you'll see that we've got a heap of different options for our trend line. The second one down is linear, and that's what we've currently got. So that looks like a straight line. Now we can extend that forward and backwards if we like. We can display an R squared value, which is a correlation. That tells us how close our data is to our function and how accurate our function is essentially. Now our R squared value here is 0.93, which isn't too bad. Now I'm going to go back to our trend line, if I can. If I can. Trend line options. Hopefully it lets me change the trend line. Might just delete the trend line for a second, re-go through it. So that's one option with our trend line. Once we get add a trend line, what we can do is we can display the equation on the chart. And that there, I'll try and make this as big as I possibly can, y equals 0.069x minus 0.12. That's in the form y equals mx plus c. Our gradient is 0.0068 there, and that tells us that for every degree we increase our velocity or our speed 0.0068 meters per second, and the c value tells us where that should intercept. Now that also tells us that we might have a little error with our testing, or there might be some factors that we haven't considered, as that is below 0, which we'd expect our function to be at. Okay, we know that the mousetrap doesn't stop at 0, but that would be a good point to talk about in our discussion. As I said before, this is probably not a linear equation, however, though, and I've set the data up intentionally so that's the case. And what I want us to do is to look at some different types of functions. So the first one we have here is a logarithm, and we can again display the equation on the sheet. That doesn't make any sense to us right now, but that displays a logarithmic relationship, and we'll figure out more about that in year 11 and 12. And that's a far, as we can see from our R squared value of 0.9774, that's a far better matched equation. Alternatively, we can look at a polynomial in the order 2, that's a quadratic. If we grab our data there, we can see that that is far closer and more effective at matching our data. So we can say that inside the domain of 0 to 180, the mousetrap converts elastic potential energy to kinetic energy with the relationship as per our screen. Now, that is all we would need to be able to do at this stage in year 10. What I'm going to do now is show us how to deal with a linear equation, some far kinder data. So I've got over here mass versus acceleration. I'm going to grab all that data. I'm going to again insert a graph, a scatter plot. Okay, that data looks far more linear, still not perfectly linear, but I'm going to add a trend line. I'm going to make it linear, and I'm going to display our equation on the chart. If I wanted to exclude some data, okay, I could create two graphs, one with my outlier down the bottom here and one without my outlier down the bottom, and just see how that affects my data. What I can see there is that my gradient is negative 1.5143, which means that as my mass increases every kilogram, my acceleration goes down. So if I was to add 1 kilogram of mass, I would lose negative 1.5143. As we started at 0.53, that would mean it is essentially stopped. And that explains a relationship that we sort of expected when we're doing this, as we know that F equals ma. So as we increase the mass, we would expect our acceleration to decrease. That is how we create graphs on Excel and trend lines on Excel. I will show us graphical now.